Section 1.5, more on slope. We're going to find slopes and equations of parallel and perpendicular lines, some Algebra 1, Algebra 2 concepts, even seen in geometry as well. We're going to interpret slope as a rate of change, and we're going to find a function's average rate of change. This is something that's definitely going to be new to PreCalc. So in general, slope and parallel lines. It says if two non-vertical lines are parallel, then they have the same slope. If you remember, slope talks about a rise over run. So in regards to taking an equation, if I had a line that increased by 1, I had a slope of 1, a line that would be parallel to it would also have the exact same slope, where it would rise and run at the same rate. They have the same slope for parallel. It says if two distinct non-vertical lines have the same slope, then they are parallel. Remember those non-vertical lines? They're going to have the same slope. They're still going to be parallel. It says two distinct vertical lines, both with undefined slopes, are parallel. Since we cannot say undefined slopes are equal to each other, they just state that if you know you have two vertical lines that have undefined slopes, they're still going to end up being parallel, even though their slopes are not technically the same. So for an example, it says write an equation of the line passing through -2, 5 and parallel to the line whose equation is y is equal to 3x plus 1. We'll express the equation in point slope form. So they didn't even ask for the y equals, which is the majority of the work. All right, so if we see that it is parallel, we're going to go over to this equation. It's slope-intercept form, which means we can just identify the slope. In this case, since the slope is 3 and we're parallel is the same slope, we're just going to use a slope of 3, and we're going to use this x1, y1 value. We're going to take it to point slope form. That means we have our y minus y1 is equal to m times x minus x1. And we have a y minus a y1 value of 5 is equal to a slope of 3 times an x minus an x1 value of -2. So if we minus a negative, we're going to add 2. They just said point slope form, so we're done. If they wanted slope intercept, distribute, solve for y equals. Now, slope of perpendicular lines. Parallel lines have the same slope. Perpendicular lines have a different kind of slope. The different kind, it says if two non-vertical lines are perpendicular, then the product of their slopes is -1. The product of their slopes is -1. What that means is you probably would have learned perpendicular. If you had a slope of a 1/2, to make that different, you would have ended up taking and flipping the fraction and changing the sign. We would have learned to use negative or opposite reciprocals. So when you learned about perpendicular lines, you would have learned the phrase negative reciprocal or maybe an opposite reciprocal. What you do is you take the slope, you invert it, so flip it, and change it to the opposite sign. So if we were to take a 1/2 and multiply by that -2/1, that's where they're getting this product is -1. It says if the product of the slopes of two lines is -1, then the lines are perpendicular. Number 3 says a horizontal line having 0 slope is perpendicular to a vertical line having an undefined slope. Again, we can't have a negative reciprocal of a 0 slope, right? It just doesn't make sense. And if we have an undefined slope, we don't know what it is, so how would you take a negative reciprocal of that? We just state, if we know we have a horizontal line, we know we have a vertical line, those are going to have perpendicular, they're going to create perpendicular lines, which means that we have negative reciprocal slopes. So, as I kind of said before, they need to have the negative or opposite reciprocal slope. For example, it tells us to find the slope of any line that is perpendicular to the line whose equation is, they give us the general form, x plus 3y minus 12 is equal to 0. So in order to see what my slope of perpendicular lines are, obviously we need the slope. So we're going to find the slope, and then we'll make the negative reciprocal of it. So if we solve to get y all by itself, right, you want slope-intercept form. If I wanted the 3y all by itself, I can move the x and move the 12, or I can just move that 3y, that little shortcut we looked at the other day. So x minus 12 is what's left over. X minus 12 is equal to a -3y. If I divide by that -3, we end up with a -1/3 x and a +4 as our slope-intercept form. All we need is the slope. So if I have a -1/3, I would need the negative reciprocal of that. So if I flip it and turn it into the opposite sign, the slope that we need for this is going to be any equation that has a slope of positive 3 is going to be perpendicular to that given general form equation. Now, slope as rate of change. Slope is defined as the ratio of the change in y to the corresponding change in x. We talked about that little delta y compares to delta x, right? Change in y compared to change in x. It describes how fast y is changing with respect to x. For a linear function, slope may be interpreted as a rate of change of dependent variable per unit change in the independent variable. Again, change in y over change in x, the change in the output compared to the change in the input. So for example, it says in 1990, 9 million adult men in the United States lived alone. In 2008, 14.7 million adult men in the United States lived alone. Use this information to find the slope of the linear function representing adult men living alone in the United States. Express the slope correct to 2 decimal places and describe what it represents. So if we were to take a look, in 1990, we had 9 million adult men. So what is our input? We're talking about input of the year 1990. We're going to output 9 million adult men. In 2008, input 2008, we're going to output 14.7 million adult men. So if we find our slope, right, m is equal to, we have that y2 minus y1 over x2 minus x1, or a change in y over change in x. So if we have our 14.7 take away 9, compared to that with the 2008 take away 1990, 14.7 take away 9 is going to leave us with 5.7. And if we divide that by the change in our years, we're looking at 18-year change from 2008 down to 1990. And we throw that into our handy-dandy calculator, we get approximately a 0.32. So it wants us to express the slope to 2 decimal places and then describe what that represents. Well, that means go back and pull the words. We have a change in y over change in x, a change in the output. The output is talking about the number of millions of adult men. So that means we're going to have a 0.32 million men per, our x value is talking about what year? So per year. So now getting into some stuff that we haven't done prior to pre-calc. The next part talks about the average rate of change of a function. So we know what rate of change is. It's a change in y compared to change in x. It's going to be very similar to that, except we're going to evaluate some functions to find that change in the y value. So it says let x of 1 and f of x of 1, meaning the answer to the function evaluated at x of 1. And we have x of 2 and the value of the function at x sub 2 be distinct points on the graph of a function f. So they want you to take a look at that little picture down here. It says that the average rate of change of f from x1 to x2 is denoted by the change in y over change in x, read delta y, divided by delta x, or the change in y divided by, that should have been not divided by, the change in x. So if you take a look, they have given to you a function that is a curved line, right? That blue kind of curved line. They want to figure out the average rate of change between those 2 points. So we are looking at these 2 points on the graph, and we want to figure out what is the average rate of change. So this is how we start getting into some of that calculus kind of stuff. You eventually will be able to determine the rate of change at every single value along this curve to figure out what's happening with that graph. But for right now, we're just going to take and ballpark from the starting point of x1 to this ending point of x2, what is that average change as we're starting from point 1 to point 2? And the way that we do that, and they call this a secant line, because it's taking those 2 points and it's just drawing straight in between the 2 of those. So what they're telling us that we're doing is we're taking our change in y compared to change in x, but instead of just having a y2 minus a y1, we're going to evaluate a function. We're going to plug that x2 value into a function and get the output value. And we're going to take an x1 value, we're going to plug it into a function, and we're going to find out what the y value is. So they're not going to give you the y2 and the y1. You have to evaluate to get those values. So let's take a look. Let's try an example. So it says to find the average rate of change for f of x is equal to x to the third from x1 of -2 to x2, 0. So we're going to start by figuring out, again, we have that change in y compared to change in x, the change in y compared to change in x, the change in our function compared to the change in our input. So that means we are going to take and find the value of the function at x sub 2. That means we're going to find the value of 0. We're going to take away the value of the function at x sub 1, which is -2. And then we are going to divide by our x2 minus our x1. So we'd have a 0 minus a -2. So that means we need to go and figure out what is the value of the function at 0. That means I'm going to go up here and I'm going to figure out what is 0 to the third power. 0 to the third power gives me 0. I'm going to take away the value of the function at -2. So again, I'm going to take this x to the third power. I'm going to take a -2 to the third power. -2 times -2 times -2 is going to give us a -8. So the change in y is based off of the answer to the value of the function. The answers, the output values. So now I have a 0 minus a -2 still on the bottom. So evaluate that down. On the top, if we have a 0 minus a -8, we end up with 8. If we have 0 minus a -2, that gives us 2. And we're going to end up with 8 divided by 2, which gives us 4. So the answer to this, the average rate of change, is going to end up being a 4. Now, if you think about it, x to the third power, that's when you're looking at that graph that kind of makes a parabola shape to the top and a parabola shape to the bottom, and you're looking for that average rate. That's where we draw that secant line, that straight line. Okay. Now, what happens if we have an average velocity of an object, a velocity looking kind of at a speed of something? So it says, suppose that a function expresses an object's position, s of t, in terms of time t. An average velocity of the object from t1 to t2 is the exact same setup. Instead of having f of x2 minus f of x1, we're not looking at function f of x, we're now looking at that s of t. We're talking about the position in regards to time. So that means we have the change in the position, the change in s, compared to the change in time, delta t. So the value of the function s of t2 minus s of t1 is going to be divided by the change in time, t2 minus t1. Exactly the same as what we just did, just different notation because we're talking about position and time versus just a regular f of x function notation problem. Take that out. All right, so if we were to look at an example, it tells us that the distance in feet traveled by a ball rolling down a ramp is given by the function s of t is equal to 4t squared, where t is the time in seconds after the ball is released. Find the ball's average velocity from t sub 1 is equal to 1 second to t2, which is 2 seconds. So what is the average speed from 1 second to 2 seconds? So we're going to take our change in s compared to our change in t, which means that we are evaluating, we have two pairs, two values that we're looking at. We're looking at t2 of 2 and a t1 of 1. So we need to evaluate our s function at 2 and evaluate our s function at 1. And then we are going to divide that by 2 minus 1. The value of the function at 2 minus the value of the function at 1 over 2 minus 1. So now if we were to start by taking our s of 2, that means we're going to go up to our equation and we're going to plug in a 2 for t. So I'm taking 4 times 2 to the second power. I'm going to take away s evaluated at 1. So now I plug in 1 for t, 4 times 1 squared. And I'm going to divide that by, we still have that 2 minus 1 on the bottom. So if we simplify some of this down, 2 to the second power is 4. 4 times 4 is going to give us a 16. Take away. 1 to the second power is 1. 1 times 4 gives us 4. And then we're going to divide by, well, at this point, 2 minus 1 just gives us 1, right? So 16 minus 4, that's going to end up giving us 12. Well, what does that mean? We're going to end up with 12 feet per second. They wanted us to find the ball's average velocity. Average velocity, what is the change? We have feet per second. Now, it wants to know, using the same function, we're going to change up, instead of going from 1 second to 2 seconds, we're now going to look at what is that rate of change from 1 second to 1.5 seconds. So we're going to plug it in the exact same way that we did. Again, we're finding the change in S compared to change in T. That means that we're going to evaluate the function S at 1.5. We're going to evaluate the function S at 1. And we're going to divide by our 1.5 minus 1. So the value of the function at 1.5 means that we are going to take 4 times 1.5 squared minus 4 times 1 squared and divide it by 1.5, take away 1. So if I take 1.5 to the second power and then I multiply it by 4, that's going to give us 9. If I take 1 to the second power times 4, that gives us 4. And if I take 1.5, take away 1, I'm at a 0.5. So 9 minus 4, that gives us 5 divided by 0.5, which is going to give us 10 feet per second. So if you think about it in regards to the situation, right? Between 1 and 2 seconds, 1 to 2 seconds, we're going 12 feet per second. When we're going from 1 second to 1.5 seconds, I kind of broke it down a little bit, we're only going 10 feet per second. So if you think about a ball, as it is rolling down this ramp, it's going to be picking up speed. So the speed is going to get faster. So from 1 second to 1.5, it was only going 10 feet per second. Once we got from 1 to 2 seconds, it's going 12 feet per second. It's just showing you that as that ball is rolling down that ramp, it's going to pick up speed. It's going to have a faster pace the longer it travels down that ramp.